So when we're solving systems in terms of three variables, it's actually not different in terms of process, not really different from the two-dimensional case. It's just that because you have more pieces to chase around, our algebra gets a little bit more complex. There's usually more steps involved, but the steps follow along the same logic. And for that matter, if you want to use substitution for this, you could, but remember the idea of substitution is to take one variable out and leave yourself with a single equation in terms of one variable to solve. In order for that to happen here, because we have all three of x, y, and z, you would need to be able to replace two of them to isolate a third. And as we saw in our last section, it's not always obvious how you'd want to replace one. So being able to get rid of two isn't really something that you can reasonably expect, at least not with any consistency. It can certainly be done, and if you want to use substitution, it's perfectly valid. It's just, it tends to be more work than you'd want to do, and for that matter, using elimination or addition instead builds towards a natural extension that you can get from this material that if you choose to do the extra credit, you'll see more of in Chapter 6. Anyway, if we're going to follow through with this method, like I said, it's very much the same as before, where when we're dealing with these, what we want to do is reduce the system to two equations and two variables, where essentially you're doing some sort of addition to cancel out the third from both pairs, then solve the resulting system of equations to be specific, using whatever method you want. At that point you've got two, so substitution's back on the menu, where the result in one variable will give the value of the variable. Then back substitute what you got from step 2 into your equations from earlier to get one of the other variables, and then use the two that you have from there to get the last one, where final step we're not always going to go through is to check your work. So let's get an example here, understanding how we can use this slightly modified process for a system of three variables. So for this, we want to solve the system x plus 4y minus z equals 20, 3x plus 2y plus z equals 8, and 2x minus 3y plus 2z equals negative 16. So our first step when trying to solve a system like this is to essentially try and remove our third part, because, well, 1 is not enough and 3 is too many. A lot of what we work with, a lot of what we're more comfortable with is doing things in terms of two variables and two equations, so we're going to try and get rid of one of our variables, and hey, look at that. It's actually very convenient in this case to be able to do so, because we can see the coefficients of z, that third variable, happen to be negative 1, 1, and 2. Which means that if we want to do some sort of elimination, saying there, z is a natural candidate to remove. Where if we want to deal with that, if we want to get rid of z to reduce our system down by one variable in one equation, we can start by adding the first two together directly, that is x plus 4y minus z equals 20 plus 3x plus 2y plus z equals 8, where that would cancel out the z's and leave us with 4x plus 6y equals 28. And then in the second case, if we want to get rid of the 2z down there, we could multiply the first by 2 and add that to the third. So we would have 2x plus 8y minus 2z equals 40, plus 2x minus 3y plus 2z equals negative 16, leaving us with 4x plus 5y equals 24. And then at that point, we'd be able to reduce that system down into something like 4x plus 6y equals 28, and 4x plus 5y equals 24, where we can solve by elimination really nicely there because the 4x's line up really well. Multiply the bottom by negative 1, add, and we would cancel out the 4x's and be left with a y equals 4. And then from there, hopefully it's pretty straightforward how we can go in reverse to get what we want, because if we have y equals 4 as our starting place, we can then plug this into really any of the equations we want. So I'm going to pick the second one here. We would have 4x plus 5 times 4 is equal to 24, or pull over the 20, divide by 4, and what you would have is x is equal to 1. And then to get z, you do the same sort of thing. You can plug that into any of our equations. I'm going to pick the third one here for absolutely no good reason. But for that, what you would end up with is something like 2 times 1 minus 3 times 4 plus 2z is equal to negative 16. And you can pull our terms around a little bit more here, move some of these positives and negatives, and what you would end up with is that z should end up being equal to negative 3. So that's our third coordinate. Here's our x, there's our y. So our solution, if you want to express this as that sort of ordered triplicate in solution set notation, would be 1 for x, 4 for y, and negative 3 for z as our final triple of values there. But again, the process was very, very similar to what we've done before. You eliminate one thing that you don't want using addition, then you just have to do it again to make sure that things match up properly, and from there it's a, I wouldn't say simple, but nice-ish 2x2 system. Follow through whatever method you want to get the answer. In this case, I suppose you could have done substitution, but with the 4, 6, 28, and 4, 5, 24, you would have had something not so nice and rational to chase around in there, and you still would have ended up here anyway. But once you get to this point, you can do what you want, because those systems should be a bit more approachable. Anyway, this is basically all we have here, so we're going to finish this section with another applied example.